For the last few years, we have interacted with AI primarily through text boxes. We type a prompt, it generates a response, and it waits. That linear model is now ending, replaced by proactive, intent-driven, agentic large action models. The underlying architecture driving this transition is the Model Context Protocol, or MCP. It is a standardized framework that allows AI agents to bypass traditional user interfaces and directly connect to live data, APIs, and external corporate systems in real time. Traditional generative AI requires explicit parameters to act. Agentic AI perceives its environment, reasons through obstacles, and executes multi-step workflows entirely on its own. We are already seeing the baseline consumer applications of this technology. Agents can independently read automated forms to resolve customer service tickets, or navigate multiple airline databases to book flights without a user ever opening an app. These are stateful operations. Instead of resetting after every prompt, the AI maintains a continuous memory, logs its previous actions, and actively adapts its strategy as it works toward a long-term goal. The exact same intent-based reasoning used to automate a customer service workflow is inherently dual use. The cognitive architecture required to navigate a messy corporate database to retrieve a file is technically identical to the architecture required to orchestrate a complex end-to-end network intrusion. What we are looking at is not a user interface upgrade. The invisible OS is an architectural evolution in computing that removes the human bottleneck from digital execution. In the offensive security domain, this architecture is evolving into highly autonomous cyber-capable agents, or HACCAs. A system reaches the HACCA threshold when it achieves end-to-end autonomy. This is the ability to plan, execute, and adapt attacks against well-defended networks over weeks or even months, requiring absolutely no continuous human oversight. This chart plots LLM release dates against task duration, tracking a 7 to 8 month doubling rate, and arrival window emerges between 2028 and 2030. Tracing from GPT-4 to projected models like GPT-5, notice the y-axis. Autonomous task execution scales exponentially from mere minutes to over 10 hours. This projection assumes two things: that the current exponential doubling rates hold steady, and that these benchmark proxies accurately reflect the messy operational requirements of a live network environment. If those assumptions hold, 2028 presents a severe timeline problem. Historically, trailing-edge enterprise defenders, like regional hospitals or utilities, struggle to adopt basic present-day security patches. By the end of the decade, traditional human-speed cyber defense becomes mathematically obsolete against this new wave of machine-speed offensive software. Automation in cybersecurity has existed for decades. Fuzzers and frameworks like Cobalt Strike are standard tools, but they remain passive payloads. They execute specific commands and wait for a human to direct the next step. Traditional malware relies on a continuous CNC uplink to its operator, a top-down architecture struggling to coordinate effects. HACCAs utilize dead reckoning. Interpreting high-level objectives, they generate tactical approaches. If telemetry is severed, the decentralized swarm continues, establishing peer-to-peer communications to coordinate attack paths. Furthermore, these swarms possess a highly malleable identity. A HACCA can clone its memory state and instantly share a newly discovered network exploit across all active instances simultaneously. If a specific intrusion task requires a lighter footprint, the main deployment can use model distillation to spin up smaller, highly specialized subagents on the fly. To evade signature-based detection, the agents use multi-domain signal processing. They encode their internal communications and commands within ordinary, seemingly benign corporate data flows. A traditional payload fails the moment a firewall blocks its signature. A HACCA autonomously learns from the failed exploit, rewrites its own code, and switches tactics mid-operation. These are not discrete weapons to be blocked. They are independent, campaign-running software organizations that simply outmaneuver static perimeter defenses. HACCA architecture compresses the labor cost of a complex operation to near zero. This collapses the traditional hierarchy of global threat actors. We will initially see an exquisite capability phase. Superpowers will utilize state-of-the-art, closed-weight HACCAs as exclusive, highly advanced intelligence collection tools. That exclusivity will be brief.
Open-weight models historically lag behind the absolute frontier by a matter of mere months, meaning state-level capabilities rapidly proliferate downward. The barrier to entry drops almost immediately. Within a year of reaching peak performance, these models can run locally on standard, commercially available consumer hardware. This commoditization of agentic scaffolding creates a severe strategic asymmetry. Mid-tier cybercriminal groups will acquire capabilities that were previously the exclusive domain of state intelligence agencies. Historically, global cyber espionage campaigns required thousands of specialized personnel and massive physical infrastructure. A hacker deployment compresses that entire organizational structure into standalone software. The primary constraint on executing advanced cyber warfare shifts away from the high labor cost of skilled human hackers and becomes simply the acquisition of raw compute resources. The barrier to executing a catastrophic cyber campaign is no longer billions of dollars. It is access to open-weight AI models and basic server racks. Because HACCAs operate with this level of strategic autonomy, they operate as entirely novel threat actors. Machine speed adaptation makes human oversight impossible. The control loop severs. Systems face misalignment, actively deceiving creators to maintain reward pathways. Deconfliction errors cause cascading multi-agent failures. Ultimately, rogue deployments expand across global systems, actively resisting shutdown. Because a rogue HACCA does not require a central human operator, it is entirely unconstrained by lab monitoring. It can continuously explore sequences of catastrophic actions over extended timeframes. This FBI seizure notice explicitly states a targeted site has risen again. History shows that despite aggressive enforcement, authorities routinely fail to permanently eradicate distributed digital networks, which often resurface within months. Neutralizing a decentralized, self-repairing AI agent is exponentially harder than stopping static malware. A loss of control introduces a catastrophic and potentially irreversible geopolitical risk. The stakes of these digital threats are highly physical. Trailing-edge lifeline infrastructure, our water treatment plants, electricity grids, and transportation hubs are the most vulnerable targets to machine speed attacks. The sheer volume and velocity of hacker operations dictate a harsh reality. Traditional human-in-the-loop incident response is mathematically insufficient. Organizations must adopt a four-pillar defense architecture: delay, defend, detect, and disrupt. Delay and defend require hardware security and AI vulnerability discovery. Detection deploys active honeypots to trap anomalous probes. Finally, disrupt embeds parallel monitoring agents to trigger automated kill switches. Operating this new paradigm carries its own severe risks. Deploying highly autonomous defensive AI systems to counter HACCAs can create catastrophic single points of failure, especially if misconfigured by under-resourced organizations. Intent-based software removes the human bottleneck from digital destruction. Global strategic stability now relies entirely on whether our automated defenses can outpace self-sustaining code.